let's take a look at your homework from last time. Page 48, you had questions 2022, or 2021, 22. Question number 20 said, state Archimedes' principle, and Kendall, what did you put?
Archimedes' principle is the buoyant force acting on a body submerged in a liquid and is equal to the weight of the liquid displaced by that body.
Well, Archimedes' principle states that, blah, blah, blah. Yes, yes. All right, good. Number 21. Which objects rise, which sink, and which remain motionless after being fully immersed in water? Michael.
Objects heavier than water will sink, ones lighter than water will float, and those equal to water will stay the same.
Say that one more time.
Objects heavier than water sink denser.
That's the key, right? Because objects heavier than water will sink. Well, I'm heavier than water, and yet I don't always sink. So denser than water, more dense than water will sink. Continue.
Objects less dense than water will float, and those with an equal density to that of water will stay the same.
There we go. Number 22, kind of on the same note of what Michael had said, why does an iron ship float? Because an iron ship is incredibly heavy, and for that matter, iron is more dense than water. So how does an iron ship float, Audrey?
An iron ship floats because the density of the ship is less than solid iron, and the weight of water displaced is as great as the ship's total weight.
There we go. Good. It's basically because the ship isn't solid iron, right? There's a lot of airspace, which makes the overall density less than the density of water. Good. All right, let's go and review some things. We'll talk more about that really actually next week. So it's kind of a preview of what's coming next week. But so Michael, you don't need to be highlighting right now. Put the highlighter away. No, I got onto your brother bag. Y'all do this highlighting. I'm like, even you too the other day. Stop it. Wait till I tell you to mark something. Good grief, people. Anyway, trying to help you with success in life, and success is focusing on the moment. Let's go and review some things we talked about. We're talking about liquids, specifically really focusing on liquids at rest. What is that term, Michael? Hydrostatics. And we said that as a liquid is at rest, there is a push that liquid exerts on everything it touches. Of course, we call this push force, and this push is always what direction? In what direction is the force exerted by a liquid?
No.
Sometimes. Michael? Normal. So it could be downward, or it could be upward, it could be sideways, it could be at an angle. It's just perpendicular to whatever the object is. So what direction is liquid's force exerted? Normal to any surface that it happens to touch. We said that this force per unit area, if we took an amount of force but broke it down the amount of area in question, that would give us pressure. Good. And by the way, what's our unit for force? And our unit for pressure? Pascal's. Good. How are they related? What's that equation that relates force and pressure to each other, Audrey?
P equals F over A.
Good. P equals F over A. And this is the definition of pressure. Pressure is force per unit area. I'm not sure why I didn't think to erase this. This is not your homework. This has nothing to do with you. This is old news. It is 8:26 though, so I'll leave that up. Anyway, we said for liquid force, if we wanted to find the force that a liquid exerts downward on the bottom of a container, we would use what equation, Kendall? So far, so good. Good. What if we wanted to find the pressure exerted downward on an object in a submerged in a liquid, Michael?
F.
The pressure.
P equals.
Audrey?
Rho G.
Rho G. So we just take the A out. We've divided the area out of the force. If we wanted to find lateral force, the force exerted on a side wall of something, what's that equation? Back to Michael.
F equals 1/2 A over GH.
There we go. And what about lateral pressure, Audrey?
P equals 1/2 Rho GH.
There we go. This equation right here, Kendall, we gave it a name. It's called the... Anyone?
Law of local
law of liquid pressure. And really the biggest implication we said is that pressure depends on depth. And we talked about some different applications of that, but that's the biggest thing that pressure will depend upon. All right, let's take a look at the math problems now. Here, number 2, go and read that problem for us, Michael. Page 48. Number 2, actually, he doesn't have his book open yet. He had set it aside. I might have even said it's Friday, can't talk. Michael, read number 2.
A column of water exerts a pressure of 100 pascals and a force of 2.40 newtons. What is the cross-sectional area of the column?
All right, so we're given a pressure, 100 pascals. We're given a force, 2.40 newtons, and we're asked about an area. What equation are we going to have to use, Michael? P equals FOA is correct. He's tired too. And we want to solve for the A, though. And since it's in the denominator class, what do we do to get it out? Alternate. So what's our equation going to become, Michael? A equals F over P as we just switch the P with the A. So we take the force, 2.4 newtons, we divide by the pressure of 100 pascals, and we get
0.024 centimeters cubed.
Well, it would be centimeters cubed. It would be meters squared. Okay, so square units for area, and we're into the larger sample sizes now. So since newtons and pascals both involve meters, 0.024 meters squared. How many have that answer? All right, and then just the units. Okay, so just something to tuck away. And that'll be really the remainder of the year. Area meters squared. Volume would be cubic meters at this point. Had been cubic centimeters though, which is why we're thinking of centimeters. Number 4, read that for us, Kendall.
Height enters a water tank at 1.6.50 meters below the surface of the contained water. What is the water pressure in this pipe?
All right. And so what is the 6.5 meters? It's the only number in the problem that they gave us, Kendall. What is that?
The depth.
It's the depth, or we would say the, because we don't have like a depth anywhere in here, kind of, sort of. We have, help? Height. The H stands for height, but we understand that if you are at the pipe, and you look up, okay, there's a height of 6.5 meters above you. So height, depth, they're really the same thing, right? So although it's depth, we'll put an H here as 6.50 meters, and that's the only number they give us. They're asking for the water pressure. That's not a lot to go off of, unless you remember that we actually have a couple numbers that are assumed. After all, it's a water tank, and if we have water, we know the is
1,000
cubic meter. Kilograms per cubic meter. Was 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. We also know that as we're looking at our law of liquid pressure, we also know that
gravity
is
1.80.
anyone? Meters per second squared. Meters per second squared. It's an acceleration due to gravity. We'll talk more about that later. Yeah, so we'll just multiply all those numbers together. And we get a nice big answer here. And what do we get, Kendall?
65,700.
And pressure measured in?
Pascal.
And I do have 3, yes, I have 3 sig figs. So we'll leave it just like this. Or you might have had 6.37 E4 pascals if you had your calculator in scientific notation mode. How many one of those 2 answers for number 4? Any questions on that? Looking at number 6, read that one for us, Audrey.
Swimming pool has the dimensions length 1 times height 28.5 meters times 10.0 meters times 2.30 meters. When it is full of water, what is the force on the bottom?
All right, what equation do we need when it says force on the bottom?
F equals A rho G.
Yeah, F equals A rho GH. So to find the force, we need to take the area, density, gravity, height. Okay, so area. What shape is this swimming pool? It gives you a length, width, height. It must be what shape? It's a boring rectangle swimming pool, okay? Which is still better than no swimming pool in the summer in Georgia. It's true, but they make cool looking swimming pools too. This one isn't. Okay, just a length, width, height. Which of those dimensions are needed to find area, though, class? Length times width, right? The height isn't part of the area of the bottom. Does that make sense? So we're only going to multiply the length and the width together to get the area. So the length and the width were what again, Audrey?
28.5 times 10.
Oh, we can do that in our head. 28.5 times 10 is? All right, so we got a 285 square meter or meter squared swimming pool. The density, well, I know there's probably chlorine or pool salt or something in it, but let's just assume, Audrey, 1,000. By the time we round off our answer to sig figs, it's probably going to be just fine anyway, okay? For the gravity, again, we're going to assume, since we don't know where the pool is, we'll just take that average value on Earth, class. What is it again? Meters per second squared. There we go. And then the height or the depth of the water. Well, it does tell us the depth of the water, Audrey. 2.30 meters. It says assuming it's full of water. So we multiply all those great big numbers together. Then we get a really big number. I'm going to go ahead and put it in scientific notation. Audrey, how much force is bearing down on the bottom of the swimming pool?
6.42 to
All right, let's round it off to, was it 2 or 3? It's got to be 3. Yeah, 3 sig figs.
6.42. E4.
It was E6, wasn't it? And force measured in
Pascals.
Ooh, that's pressure. Pressure's pascals. Force is newtons. All right. Do you like fig newtons? You don't. So if somebody forced you to eat fig newtons, that would be sad. I don't know. Maybe remember force newtons. I don't know. Anyway, how many had this answer? How many had 1.48 E7, and you multiplied the height here, and you tried to work it in like it was the area? Yeah. Does that make sense now? All right, questions on this? Common mistake. Questions on this? All right, set that aside. Go and get your notes out if you would, please. And let's talk about something you read about a couple nights ago in your homework reading, and that is Pascal's principle. Pascal's principle. Blaise Pascal noted something unique. Obviously, we understand this, that as a liquid gets deeper, the pressure increases, right? Pascal was doing that experiment, remember, with those vases of different shapes and volumes, but the same depth of liquid, and found the pressure readings were exactly the same. Liquid pressure depends on depth, if it is exposed to atmospheric pressure. If the atmosphere is free to bear down, if you will, upon the liquid, that's true. The deeper you go, the greater the pressure. But if that liquid is confined, such as, for instance, in a water balloon or in a plunger or something like that, if the liquid is confined, the pressure is transmitted equally everywhere. Pascal did an interesting experiment. He had a tube with lots of little holes and little stoppers in it, and he brought a plunger down to bear upon the liquid, making it a confined liquid. No air could get in. It was trapped between the plunger and obviously the container. And as it began to bear down, he expected the plunger, the stoppers at the bottom to pop out first, right? Greater depth, greater pressure. And then gradually they would work their way up. They would begin popping out. But that wasn't the case. It was all at once. And he realized that in a confined liquid, a trapped liquid, pressure is transmitted equally everywhere. And that's Pascal's principle. If you want to write that down. Pascal's principle. Pressure within a confined liquid, that's the key, is transmitted equally in every direction. Pressure within a confined liquid is transmitted equally in every direction throughout the liquid. So you push on one part of the liquid, that force, then that pressure is transmitted equally throughout. And there's an interesting application of this principle. The book mentions, for instance, the water sprinkler. It's basically confined except for the little row of holes. How many had that sprinkler just goes back and forth, back and forth, back and and forth. I grew up with one of those. I don't have one of those now, so my kids don't have one. The oscillating sprinkler. But the idea is that little tube of water basically confines the liquid, and then of course you got that little row of holes there. Well, since it's basically confined, you get equal water pressure out of all the holes, so you get a good wide dispersion, unless of course the hole gets clogged. I think a better application is through the use of something called a hydraulic device. A hydraulic device. A hydraulic device is one that uses confined liquid to multiply force. A hydraulic device is one that uses a confined liquid to multiply force. Heavy machinery often uses hydraulics. Such as in a hydraulic lift. At the mechanic shop, they have a hydraulic lift that lifts the car. Construction equipment will use hydraulics to maybe cause extensions in the boom or something of a crane, that kind of thing. Hydraulic jack is perhaps an easier example of something. Pump on a lever, car goes up, or whatever you're trying to lift goes up. Okay, hydraulic jack is a good example. And there's a picture in your book, and I think the diagram is helpful for us. So if you would look at page 40 in your textbooks, kind of a basic diagram. I do want to talk through the diagram for you so you can see what's going on. You notice it's red, and empty spaces have kind of a darker, shiny inside red look. The black that you see would actually be something like a thick, heavy rubber type material or metal. All right, so those two black things you see labeled large piston, small piston, that's not empty space. That's trapping the liquid. And you see a couple of simple valves there, basically stoppers. And so what happens is, as the handle is lifted up, that small piston goes upward. Well, as it goes upward, it creates an opening for liquid to flow into the reservoir. You see where the reservoir is? It's just around the large piston on the outside, around that chamber. And as it goes upward, it allows liquid to drain through that little hole. The little stopper, if you will, kind of pushes forward or pulls forward just a little bit, and liquid flows in. And then on the downstroke, going to the bottom of the page now, as the handle pushes downward, that small piston pushes downward as well. Well, it forces that top valve closed, but it pushes the bottom valve open, and liquid flows into the area under the larger piston. You kind of get the idea of how those two little valves work. Really simplistic device, actually. But the key is it uses this confined liquid, this liquid that's trapped between two pistons, to multiply force. How is that? Well, per Pascal's principle, whatever the pressure is in the smaller chamber must equal the pressure in the larger chamber. So as the handle is pushed downward, it pushes on the liquid. But whatever pressure the handle or the smaller piston pushes down with, that same pressure pushes upward on the other, because in a confined liquid, pressure is everywhere the same. Does that make sense? Same pressure. But what is pressure? Force per unit area. What this means then is that the force per unit area in the first chamber equals the force per unit area in the second chamber. Well, think about this. What if you increase the area? What if this is a bigger area? For instance, let's just take some equal ratios like 3 to 5 and something like 15 to 25. All right, these are equal ratios, correct? Notice that by making a larger number in the bottom, we must also have a larger number in the top to maintain equivalence. Does that make sense? So if area is increased from one piston to the next, force has to go up with it. Does that make sense? So you exert a certain amount of force over a certain small area as you push down on the handle of the jack. The larger area underneath the car pushes up with a greater amount of force. Does that make sense? And that's how the jack is able to lift the car. So let's consider some actual numbers here. Let's get some easy numbers. We've got an 8 square centimeter area of the smaller piston. And let's suppose we push down with a force of, let's just say, 40 newtons. Let's suppose the larger piston has a cross-sectional area of, say, 25 centimeters squared. What would be the force? Well, how do we solve proportions, class? Cross multiplication, right? So if we were to cross multiply, we take the two known values here, the 40 times the 25, get that on your calculator, And hold on now, it would equal 8 times f sub 2, right? But what would we do with the 8 anyway? Divide it off, wouldn't we, to get the f by itself? So multiply the 2 known values and divide out the odd guy. So you've already multiplied 40 times 25. Go ahead and divide by the 8. How much force would be put out? 125 newtons. You put in 40 newtons, you get out 125 newtons. It puts out more force than you put in because you're also increasing the area. Does that make sense? And that must be true based on Pascal's principle. Well, here's the only thing. I don't know that I've ever looked at anything, let's just take this water bottle, right? Roughly circular cross section. That looks like it's X many square inches or square centimeters. Like who does that? When you look at a piece of pipe, have you been to the hardware store and you've seen different pieces of piping, whether it's metal sheathing or whether it's the PVC pipe? What do we look at? How big across it is, don't we? Well, about 3-inch piece of PVC or a 2-inch piece of PVC or what? Right, we look at the diameter. So I'm going to take this one step further, and I'm going to say for practical purposes, when I give you problems, I'm going to give you diameters, because that's how we think, that's how we see, correct? Well, what is area? If it's a circular cross-section, again, typically when working with liquids, we go with circular cross-sections. Well, how do we find the area of a cross-section circle? Pi r squared. Again, we mentioned that the other day. Very important to remember pi r squared. Well, the problem is that's r, right? That's not diameter. Well, how is diameter and radius related to each other? A diameter is twice the radius, correct? Therefore, the radius is half the diameter of a circle, right? So I could say that area is pi times half diameter squared. And if I square a half diameter, I get a 4th pi d squared. So we could say, don't write this down, that the force applied in one part of a hydraulic device over 1/4 pi times that diameter squared equals the second force over the 1/4 pi and the diameter of that region squared, correct? But notice, if you have the same thing on both sides of an equation, what can we do with that same thing? Cancel it away, right? So since I have a 1/4 on both sides, I'm going to cancel it. Since we have a pi on both sides, I'm going to cancel it. And it becomes f over d squared equals f over d squared. I want you to put this in your notes. It's f over a equals f over a because it's pressure equals pressure. But I want you to put this down that diameter squared is analogous to area. It is not equal to area. You don't find area by squaring the diameter. But in this particular equation, because there's an area on both sides, we can substitute diameter squared in place. And that's just going to make our work easier. And I'm a lazy mathematician. Do you all understand how and why I can substitute a diameter squared, even though area doesn't equal diameter squared? Everyone got it? All right, so let's consider this problem now. Let's suppose we have a piston that is, say, 3 centimeters across. So we've got our hydraulic jack and the piston that I am pushing down with the handle to try to lift my car off the ground, 3 centimeter diameter. Let's suppose the larger piston that's lifting up, let's just say is about that big. That would be about, let's say 12 centimeters, okay? And let's suppose I push down, I was going to use Kendall, all of Kendall's weight. Kendall jumps on top of it. Let's do that. I like, Kendall, can you lift my car? And she steps forward and she jumps on the handle without falling off, and all of the force that she's able to exert on the handle, which is the smaller piston, let's just say she weighs 390 newtons. That's all of her weight. It's like 90 pounds. Okay, pretty close, right? And the question is, how much force pushes up on the car? Depending on how much the car weighs, we'll see if the car gets off the ground or not. All right, so we're going to use what equation here for our hydraulic device? Class? F1 over A1 equals F2 over A2. Force, pressure equals pressure. But instead of area in both cases, class, I'm going to substitute diameter squared. By the way, every year, somebody forgets to square. Don't forget to square. Maybe put a star next to that and highlight. So you got to highlight. Highlight in your notes. Don't forget to square. Very important. All right, so let's plug in the numbers. In for the F1 class, we plug in.
390.
Kendall's 390 newtons. In for D1 squared, we will plug in 9. And by the way, I'm not going to write the centimeters squared because centimeters squared here will cancel with centimeters squared over here, won't it? All right? What do I plug in for F2? F sub 2. No, we don't know it. Leave it as F sub 2. All right, and then what do we plug in for D sub 2 squared? 144. Remember, when you cross multiply, the quick way is multiply the two knowns, divide out the odd gap. And we multiply and divide. How much force does Kendall put out? 6,240 newtons. That's going to be about 1,500, 1,600 pounds of force. Small car. Might lift small car. All right. She only needs a small car. It's Kendall's car, not my car. And 6,240 newtons. Only 2 sig figs though. So let's approximate, class. 6,200 newtons, we'll say, is how much force pushes up on the car. Questions on this? That's pretty awesome. Physics, right? Science, the purpose is to make your life better. I can't lift the car. Let me invent something that'll lift the car for me. Hydraulics, really amazing in the way that they can multiply force. And it almost seems a bit like a miracle, doesn't it? Right? But you know how life works. Do you ever get something for nothing? Student loan forgiveness is big in the news right now. I've talked about government, current events, student loan forgiveness. Well, wait a second. The government is owed that money. If the government doesn't get that money, the government will have to get money from somewhere. Where will it get it from? Taxpayers. Yep. And as the government takes money from taxpayers, it's also taking from businesses. And businesses start to lose money as well because they pay taxes. And their taxes go up. You know what businesses do to keep from losing money? Because they don't want to lose money. If they lose money, stockholders sell off shares of stock. Their investors lose money. They don't want the investors to lose money. So you know what they do? They raise prices. We call this inflation. Yes. So we don't get something for nothing. This miraculous multiplication of force comes at an expense. Any of you ever used a hydraulic jack before? And it's not push down, car lifts up, is it? It's push, 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 car, and finally, after pumping a gazillion times, the car finally goes up like that much. But you only needed it to go up that much so you change the tire or whatever, right? You push a lot over and over and over again, and that's why, by the way, it's important there's a reservoir of extra liquid that can keep flowing in to keep pushing up, keep flowing in to keep pushing up, okay? Because you have to keep pushing over and over again. So you push the handle down, say 12 inches, that car ain't going up 12 inches. It might go up like 1/8 of an inch, okay? It barely goes up at all, right? You lose distance, and here's why. You will get a multiplication of force because pressures are equal in both spots, right? Confined liquid, whose principle? Pascal's principle says that in a confined liquid, pressure is everywhere the same, equally transmitted, right? You push with one pressure, it pushes up with a pressure. But whatever volume of liquid you push down is the same volume of liquid that pushes up. But remember, you've got a big wide cylinder. So while you've got a narrow cylinder, you push down this much liquid, that same volume when it spreads out is like that much. Does that make sense? You push down a lot, it lifts up a little because volume 1 equals volume 2. How can we find volume? Remember I said the other day, volume of any solid shape, which the piston should be a solid shape, okay, is the cross-sectional area times height. So here's the next equation for a hydraulic device. A1H1 equals A2H2. A1H1 equals A2H2. Area times height, or distance that you push, it equals area times height, or distance of liquid that you push. Well, once again, notice we got an area on both sides, don't we? So once again, what can we substitute instead of area? Diameter squared, because the 1/4 pi's again would cancel. So let's suppose Kendall jumps on the handle of the jack, And let's suppose she pushes the jack handle down, say, I don't know, this far. Let's just say that's 22 centimeters. She pushes the jack handle down 22 centimeters. How high does the car rise? Well, we're going to take the equation class,
And then H1 equals A2 H2.
and instead of the A's, we're going to plug in diameter squared. So we're going to say diameter 1 squared times H1 equals diameter squared 2 times H2. Does that make sense? Diameter 1 squared, class, 9, times the height that was pushed down, class,
22.
equals diameter 2 squared.
144.
By the way, remember the centimeter squared would cancel anyway, times H2. This centimeter doesn't cancel yet. That's going to be the centimeter in the answer. You'll multiply these two numbers and then divide out the 144. And Kendall, how high does the car lift when you push down on the jack handle? 1.375 centimeters. Oh, rounded off, sorry, 2 sig figs. So class, about 1.4 centimeters. She pushes down this much, it lifts up that much. You're not getting something for nothing. But hey, I don't mind pushing the jack handle down over and over and over again if it means I don't have to try to lift that car. Or can I get 10 people, 10 neighbors to come help lift my car while I get under there to work? Plus the jack holds it up, right? And we'll talk about frictional forces later. But anyway, questions on the hydraulic device equations. 2 equations to know for the hydraulic device. First class,
F1 over A1 equals F2 over A2.
and
A1 over H1 equals A2 times
in each case where you see A, assuming you're given a diameter, which is what I will usually give you, you can substitute diameter squared. The book may give you areas, that's fine. I will usually give you diameter simply because that's just how we think, right? That's just the easier way to go about it. All right, look in your textbook, if you would please, at page 41, right across the page. And they give you an example here. And let's go ahead and work it together and have Michael read it for us.
The pistons of hydraulic device have areas of 4.0 centimeters squared and 10 centimeters squared. A, if the smaller is depressed with a force of 16 newtons, how much lifting force is applied to the other piston? B, if the smaller piston moves 4.0 centimeters, how far does the larger piston move?
Good. Now, by the way, ignore all of their math, okay? They do it a way that to me just, it doesn't make as much sense. So you will actually find this throughout the course. The book may have one formula. I will give you something equivalent to it that, at least in my mind, just makes more sense. Pressure equals pressure, F over A equals F over A, right? Now, technically, their equation is not wrong. It's just set up differently, but how am I going to remember to memorize that? I don't want to even think about it. Okay, so, now they actually give you areas, didn't they? Okay, so, what's that first equation we want, class? I just said it. All right, do they give us the force on the one on that first piston, class? Yes, in part A, it tells that there's an initial force of 60 newtons, and that's on the smaller piston, which has an area of 4.0 centimeters squared. Okay, and then they give me the force of the larger piston. No, that's what I'm finding. And they give me the area of the larger piston, 10 square centimeters. Notice, centimeter squared just cancel. I'm going to be left with these newtons right here. We cross multiply, we divide out at your seats how much force lifts up on the larger piston, or with how much force does the larger piston lift? 40 points, so we have the 2 sig figs and newtons. Good, Michael. All right, questions on that? Pretty easy, right? Let's take a look though, but remember there's a second equation that goes with the hydraulic device, because while we gain force, class, we lose volume. Well, we don't lose volume. Volume's consistent, and because it's consistent, we lose height or distance. We lose height or distance. What's that equation, class? Okay, same areas, right? The first area was and did it say the height or the distance that the first piston was pushed? 4 centimeters. And the area of the larger piston, again, is 10 centimeters squared. And we're finding, apparently, how much the larger piston moves. Notice these centimeters squared cancel. I'm going to be left with these centimeters right here. We multiply, we divide, and what is h sub 2?
1.6.
So we push with a force of 16 newtons, distance of 4 centimeters. It lifts with a force of 40 newtons, but only 1.6 centimeters. Questions on this? Pretty easy on the hydraulic device. All right, look at page 48 now. Page 48. And if thou wouldest, readest problem 7.0 for me. Let's see here. Audrey.
A hydraulic lift has 2 cylinders with diameters of 2.0 centimeters and 10.0 centimeters respectively. What is the force required on the smaller piston to raise a 1.3 times E4 newtons car over the larger piston?
All right, notice it never references a distance of lift, does it? It doesn't reference how far down one piston is pushed, how far up the other one lifts. So we don't need to worry about that. So the only equation we're going to need here, class, is? And let's see, do they give us areas or diameters? Ooh, diameters this time. Okay, so instead of F1 over A1 and F2 over A2, class, let's go with, yeah, let's make that a D1 squared and a D2 squared instead. All right, does it tell me how much force we use to push on, or how much force pushes on the smaller piston? No. In fact, that's what it asks, isn't it? What is the force required on the smaller piston? So I'm looking for F1 this time. Okay, do I know the diameter of the smaller piston?
10.0.
The smaller piston.
2.0.
2.0, but we're going to square it, remember? So 4. I'm not even going to write the 2 just in case I forgot to square it. All right, and then the larger piston is what's putting out the force, and it says it puts out how much force, or needs to put out what force?
1.3 times.
All right, so 1.3 E4 newtons. Okay, we need that much force to get out. So, and the larger piston diameter, so I write 100. Again, the centimeter squared we cancel anyway. All right, so we cross multiply. We'll start by multiplying here and then divide out the 100. How much force do we need to lift this 13,000 Newton car? Paula? 520 newtons, and it's 2 or 3 sig figs? 2. Yeah, we got 3, 3, and then 2 at the very last number is only 2. So yeah, that's perfect. That means I don't have to put a decimal. If I needed a decimal, I'd put it, but we only have the 2 sig figs anyway. So 520 newtons, that's just about 100 pounds of force. So again, with a little help, Kendall could even generate 100 pounds of force. We got this. Teamwork. All right. But anyway, I'm just like, I got it myself. I'm Shira. Anyway, so yeah, so, and this is an interesting problem. Is okay, do I have what it takes to lift this car based on the design of the jack that I possess, based on how heavy my car is? You can Google that, right? Do I have the ability to apply enough force to make this car get off the ground? Okay, yes we do. Get some help. And that's what Dad's for anyway, make Dad help. He got this. All right, questions on that? I think number 8's even more intriguing because now we work into a design question. How would we design a hydraulic jack? Read number 8 for us if you would, Michael.
Find the minimum diameter of the largest cylinder of the largest cylinder of a hydraulic press can have if it is to lift a 1.1 times 10 to the 4th Newton car with an applied liquid pressure of 420 newtons times square Newton. If the smaller cylinder having a diameter of 1.5 centimeters.
All right, so we know that our smaller piston is going to have a 1.5 centimeter diameter. Maybe that's just considered the standard diameter. But in our design, we know, okay, I need to be able to lift this size vehicle, this weight vehicle. When I design my jack, I'm going to make sure that the diameter of this piston is sufficient to make the lift happen. Does that make sense? So, as we look at it, we've got our F1 over, again, it's going with diameters, D1 squared equals F2 over D2 squared. I know which numbers already. Kendall?
The force on the larger piston.
Good, I know the force I need to be able to get out of this particular jack. I need F sub 2 to be
1.1
newtons. So slightly smaller car than last time, right? By a couple thousand newtons. Okay, so it's, about 500 pounds lighter. Okay, smaller car this time. What's the other number that I know for sure?
the liquid pressure.
Oh, liquid. Weird. Okay. Interesting. What else do I know?
The diameter of the smaller piston.
The smaller piston's diameter is,
1.5 centimeters.
and we know that we're going to have to square the 1.5 centimeters here. That's going to be my D1 squared. And the question is, what is D sub 2? What diameter is needed? Now, it's interesting. They don't give me force 1 either. So you see I've got two unknowns in here. But it does tell me how much liquid pressure. What is pressure, class? F over A. So can I cheat and use the D squared necessarily here? Not in this, but if P equals F over A, and I know the P, and I could find the A, couldn't I? Let's find what the force would need to be. How do I rewrite the equation solving for force, class? F equals P times A, or A times P. So I know the liquid pressure needs to be, class, 420, this is significant, newtons per centimeter squared. Pressure is 420, not newtons per meter squared, which is a Pascal, but newtons per centimeter squared. You know what's interesting here? That means my area can be in centimeters squared, which is really nice. That means I don't have to change a whole bunch of units. How would I find area? Normally, how do I find area? Pi r squared. But remember, we said we don't know the r, we know the d. So instead of r squared, class, half d squared, right? Pi times a half diameter squared. Well, the diameter is 1.5 centimeters, so the radius, half of that would be 0.75 centimeters. Let's square that on your calculator and multiply by the pi button. Now what do we get? Small little value.
1.767.
1.767, blah, blah, blah. That's your cross-sectional area. Based on the diameter, that's the cross-sectional area that we have of our little piston. If that's the area of the little piston, and we know the liquid pressure that will be in that chamber, 420 newtons per centimeter squared, which cancels, now multiply what you have on the calculator by the 420. How much force are we going to use?
742.201.
How much? 742, is that what I heard?
Yes.
Somebody else got the same thing? Okay, 742 point whatever, blah, 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 newtons. Put this in the memory of your calculator. Now, you two are good. Kendall, let me refresh your review with you how to save in the memory. Was it exactly 742?
No, it was 0.201264.
Oh, okay. So, we got to go back to the 0.75 squared. So that's your radius squared times pi. Equal. Okay. Then multiply that by the 420. Equals. There we go. That's what we need to save in the memory of the calculator. So stow 1. Now it's stowed in memory 1. So even if you turn it off and turn it back on again, when you recall 1, there it is. Okay? So it's in there now. All right. So coming back over here, this is stored in memory 1. We're ready to solve for the diameter. We're going to cross multiply in our proportion. So take a 1.1 E4. Remember the E is right above the 7 key on your calculators. 1.1 E4 times 1.5 squared. 1.1 E4 times 1.5 squared equals, and then divide out recall 1. And I just realized I didn't put it in my memory, so hang tight a second. Okay, so we have 1.5 squared times 1.1 E4. Divide out the memory value. Okay, now I got it. And what you see on your calculator is diameter squared. But I don't need the squared, I just want diameter. So now finally we'll finish class by taking the square root. What diameter? It's actually not that bad. What diameter does our other piston need to have, class?
5.774.
Yeah, 5.774 or approximately, I think it's 2 sig figs everywhere, isn't it? Yeah, so approximately diameter of centimeters, since that's what they used everywhere else. 5.8 centimeters. Now there is an easier way. You're going to hate me for this. We said that the F over A is pressure. Well, if I just went ahead and used F over A equals F over A, I could say, well, if I know the pressure is 420, I'm literally just going to put that in the F over A spot. Does that make sense? And then I'm going to say that that's equal to the 1.1E4 newtons over the area needed for the larger piston. Well, now it makes it really easy to solve for the area of the larger piston, class. Just alternate and divide, right? So go ahead and do that, and we'll get the same answer in just a moment. And notice the area of the larger piston needs to be there we go, 26.19, blah, blah, blah. Now that's the area. But remember, area is pi r squared. So if the area is 26.19, blah, 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 I need to divide by pi. Divide by pi equals, take the square root, and that's your radius. Now multiply by 2 and you got the diameter. And you get the same 5.774. So there's a couple ways to approach the problem. I feel like this is the easier approach here. But substituting a pressure in place of an F over A to me is like, let's do it the more conventional way, and then I'll show the shortcut after. Questions on either of those ways? Questions on either of those? All right, for homework this weekend, you're going to read pages 41 to 47. Read pages 41 to 47 and complete a handout. Complete a handout. Give you some practice with the math. Pages 41 and 47. Obviously, it'd be good to be looking over terms and whatnot as well, but doing this math handout. If you're watching on YouTube, the handout, there's a link in the description of the video. So click on that link to bring up the handout. We'll take a look at that in our next lesson on Monday. Have a wonderful rest of your day, and you are dismissed.